Hello. So, I'm here to talk to you about something I work on called nuclear fusion, or how you try and put the sun in a cage. So what I'm trying to do is build a better cage, basically. So I'm going to start by just explaining what nuclear fusion is and why we're trying so hard to make it work. And then I'm going to talk about what some of the material science challenges are in trying to contain this kind of reaction. And then I'll just finish off quickly by talking about some of the systems that don't get a lot of attention but are also sort of very, very important to trying to get this to work. Okay, so what is fusion? So you've probably all heard of fission, which involves uranium breaking up into smaller pieces. Fusion is right at the other end. So what you do is you take isotopes of hydrogen, so these are hydrogen atoms with different numbers of neutrons. You start with deuterium, which is hydrogen with one extra neutron. And you start with tritium, which is hydrogen with two extra neutrons. And then you smash them together, okay? And you get fusion. And then that particle breaks off into a helium atom, a single neutron, and then it releases a shed load of energy, lots and lots of energy. The problem is, trying to get these two atoms close enough together is a lot more advanced than heating up water and making it hot. What you need to do is confine them using magnetic field lines, or magnetic fields. So this is actually a device in Oxfordshire. It's probably about the same size as this room, which is actually quite small. What you can see in green, these are the magnetic field lines. It's an infrared camera, and what's happening in there is it's under very, very high pressure and it's very, very high temperatures, forcing a plasma, an ionized gas of these two atoms very, very close together and trying to get this reaction to happen. Okay? Right. So, why are we so crazy about fusion? Well, when I say it's a lot of energy, I mean it's a lot of energy. So tritium is produced from lithium, and deuterium can just be very easily extracted from seawater. And if you take one laptop battery and a bathtub of seawater, there's enough fuel in that to give one person their energy for an entire lifetime. So if coal-fired power station, you put all the coal in, it probably comes in several dumper trucks. A fusion reactor would work for an entire day, and you could put all the fuel in a briefcase and walk in with it. So it's very, very efficient when it comes to fuel. It's also very, very safe. So if you imagine a fission reactor with uranium, if there's an issue or a problem like they had at Fukushima, the problem is that you need to actively do something to slow the reaction down. It will just keep going if you leave it. But with fusion, you have to confine it at very high pressure. So if there's a problem, like in a balloon and your balloon bursts, all that gas spreads out and the reaction stops. It's inherently a lot safer than fission. And also, you may have noticed helium, neutrons, they're not very useful for building atomic bombs. So for any James Bond villains in the room, this isn't for you. There's nothing you can use here to make a weapon, okay? So this is a possible source of limitless green, clean power, which obviously is what a noble cause, I'd say. Okay, but why don't we have this already? Well, it turns out it's quite difficult. So I'm now going to just go through some of the challenges about trying to contain. Oh, something I should have mentioned. This reaction is it's how the sun is powered. So this is actually pure solar power in many ways. The sun is lots of isotopes of hydrogen crashing together, fusing, forming helium, forming heavier elements. That's where solar power comes from. So this is what we're trying to do. We're trying to create a tiny, tiny sun on the planet, effectively. And obviously that is not easy. So putting the sun in a cage is difficult. This plasma is very hot. It's approximately 100 million degrees Celsius, so really, really hot. And those magnetic fields I told you about come from magnets that have to be cooled to minus 269 degrees, which is very, very cold. That's 4 degrees above absolute zero. So the deepest, darkest corner of space is 4 degrees colder than those magnets have to be, which is not a lot. And the only way to get there is to use liquid helium, which is very expensive and very, very cold. Now, one of the consequences of this very high temperature is the reactor exhaust, which is here, down there. It's where all the atoms get pushed down to when they're in the field. It sees the same conditions, or slightly hotter conditions, as the space shuttle does on re-entry. Now, the thing is, the shuttle re-enters for about a minute. We want to keep a power station going for 5 to 10 years. So you've got to build something very, very strong to put up with that kind of thing. Now, even with all of that, the biggest challenge is actually dealing with the neutrons. Okay, so I mentioned that the reaction releases a helium and a neutron. The neutron is the worst bit. So this is a schematic of what a fusion reaction looks like. So we've got a magnetic field here. What that's doing is that's pushing back all the positive ions and the negative electrons and keeping them well confined. But neutrons don't have a charge. They just skip straight on through and fly into your reactor wall. Uh-oh. Now, they can react two ways with a material. They can be absorbed into the nucleus itself. And what this does is it changes the atomic structure and it changes what that atom looks like. This is something called transmutation. Now, if you had an atom of lead and you exposed it to the right kinds of neutrons for the right length of time, you could turn it into gold. It's literal alchemy, turning one element into another. But it's not very useful, because if you start with something that's, say, 100% tungsten, after 5 years it's only 95% tungsten. And this is quite a unique challenge, that whatever materials we put in aren't coming out the same. Okay? They also do other things that are just as bad. So they put defects into our material. So metals are all crystalline. That means every atom has a site that we want it to sit on, and it's ordered. Okay? But this neutron comes crashing in with a huge amounts of energy, and it knocks that atom off its site. Okay? So now what we have is a gap in the lattice, and we have an atom sat in between a load of others where we don't want it. And the problem is those defects, they conglomerate, they join up, and they can create even bigger defects. And what these do is it embrittles the material. So something, when you put it in, is really, really strong, and it won't bend, and it's great. And then after some time, if you hit it with a hammer, it just shatters like glass. Obviously not very good for a reactor. And one of the most sort of striking effects of this is something called radiation-induced swelling. So this is a piece of stainless steel that was put inside a fission reactor that also has neutrons, but less and a lower energy. And this is it after 5 years. And it's gone through, it's only small, but it's gone through a 30% increase in size. And that's because of all these gaps that have been put into the lattice. And then that atom there basically doesn't like sitting here, so it moves around and it goes to the edge. And over time, your component gets bigger and bigger. So imagine building a pipe, and then after 5 years, it's 30% bigger. That's not good. So what we need to do is we need to find clever ways to avoid these effects. Okay? Right. That's the bad news. Now, how do we get around those, those problems? Okay, so how does a reactor look? Well, this is a schematic of where the magnets go, just to give you an idea. So this is a tokamak. So tokamak is the most common example of a fusion device, and it's covered in magnets. So you have magnets going around the plasma. You have magnets going around the device, then you have a magnet going straight through the middle as well. Magnets everywhere. And that's because containing a plasma is very, very difficult. Okay? And this is a model of a cross-section of a device called ITER, I-T-E-R, which is currently being built in the south of France. You may have heard about it on the news. Very, very big, very expensive, very impressive piece of technology. But that's a man down there. So that's how big this reactor is. It's very, very big, and it's very, very complicated. Now, this is the sort of donut where the plasma will be, and then just around here, that's where all the technology I'm about to talk to you has to go. It has to fit into a very tiny space, so it's very advanced. And the other thing to point out, the other important component, this bit here, that's called the diverter. That's the exhaust I was talking about, and I'll get to that slightly later. It's quite an interesting challenge. So what does the cage look like? Well, the first bar of the cage has to be the magnetic field. That's containing all our neutrons or our electrons, so that's good. We don't have to worry about that. Magnetic field can put up with anything, except neutrons, as I said. The problem is that these atoms, they don't stay confined. They eventually diffuse to the edge, and then when they get to the edge, they fall down. And that's where they go to the diverter. That's why we need an exhaust, because that's where all these atoms end up. They hit it at tremendous speeds, incredibly hot. And even with the best sort of plasma physics going, the coldest they've been able to get to it is 800 degrees. So that's the temperature we have to deal with. Minimum, absolute minimum, 800 degrees. And then you have the first wall, which is around here. All the way around, you have a similar material. Slightly cooler, so that's good. Just behind the first wall, you have to have a lithium blanket. Now, I'll talk in a sec about why we need lithium, but basically this is where we're getting our tritium from. So tritium's actually quite hard to get hold of, generally. And what we need to do is find a way to produce tritium within a reactor. So that's what that is. You then have a vacuum vessel, and that keeps outside air away from inside air. You need to keep them separated. Then you have your magnets, and these are the really complex bits. So you have your really big magnets that confine it, but then you also have very small magnets that are there to control instabilities in your plasma. So this is a very, very chaotic, difficult piece of science. So you need lots of sort of steering magnets to try and keep it under control. And these all need to be kept very, very cold. Remember, this is 800 degrees. This is about 30 centimeters. So this, when we build it, will be the steepest temperature gradient in the universe that we know of. It will be the temperature of the sun and then the temperature of deep space right next to each other. So that's a very unique challenge. Then right at the end you have a cryostat, and that's to keep the temperatures all confined. Because all the way through you have to have cooling pipes, keeping everything the right temperature. These blankets, they have to be 100 degrees, 200 degrees, you've got to keep them cold. Magnets, you've got to keep them very, very cold. And then on top of that, you have other systems. So you have diagnostics. We need to know what's happening in this plasma. We can't just let it go. We need to be measuring it at all times. Cooling, as I've said, robotics. Once this is going, you can't put a person in there. If a tile falls off, we've got to have a robot that's able to go in and pick that tile up and screw it back on. So actually some of the most advanced robotics that's come out in the last 5-10 years have come out from Oxfordshire at the Cullum Centre for Fusion Energy, which is just down the road where the current biggest tokamak is. So that's a big area. Heating systems, you don't get to 100 million degrees using the same technologies in an oven. You have to use very advanced lasers, particle accelerators, that kind of stuff to get the temperature up. And then fuel processing. Not all of this fuel actually reacts. Some of it will just sit around here, buzz around for a bit, and then it comes out the diverter. And we need some way of separating the tritium and deuterium and then pumping it straight back in because we need to keep it in there, yeah? And then finally, turbines. This is old technology, but still very, very useful, turning all the heat we're generating into electricity. That's the essential bit, okay? And this is all in a very short space of time, maybe 5 meters, all of that technology in one place. Okay, lithium. Now, tritium is radioactive. It has a very, very short half-life. It's only about 12 years. So if you started with a cup of tritium, after 12 years, you would only have half a cup of tritium. And that means there's no natural source on Earth. If we want it, we have to make it ourselves. And the way you make it is using that pesky neutron I was talking about earlier. What you do is you pile that neutron into an atom of lithium, it fuses, and then it splits off into a helium atom and into a tritium atom. That's the good news, because that problem neutron can now be useful. The problem is making it happen fast enough to be useful. And the other, even better bit, is this reaction actually releases even more energy. So we actually get an extra 20% of energy just from breeding tritium that we can then use to generate electricity, which is great news. Yeah, as I said, these neutrons, they're very precious. And when you're designing a reactor, you have to make sure there isn't anything absorbing them, or not too much absorbing them, because you need them to be reacting with lithium. This is a design for a lithium blanket. And the idea is you mix your lithium with lead, so it liquefies, and then you pump it through these pipes. Whilst it's close to the reactor, neutrons react, it turns to tritium and helium, then it pumps back around and you can extract it. The problem is lithium lead is not a pleasant material and it's highly corrosive. How do we protect our components for 5-10 years? We don't have an answer for that yet. So also, what do we do if it solidifies? This reactor isn't going to be going all the time, it's going to shut down, at which point, how do we stop the lithium and lead just solidifying in our pipes? It changes size when it solidifies, it's going to break the pipes. Big challenge, not solved yet. They're still designing this, they don't really know how they're going to do it yet. The magnets. Now these are actually, superconducting magnets are quite old technology. These date back to the 60s, but they're very important. It bears talking about. They're niobium-3 tin, intermetallic, and they, as I said, superconduct at very, very cold temperatures. This is a cross-section of them. So they're very, very thin wires that are then held together, and then this is a pipe where they're going to pump liquid helium down it. What's really important is we protect them. So this is shielding. Okay, and that protects them from impact because these are very brittle. If you flicked one of these, it would break. It cannot put up to it any stress whatsoever. Even a small impact would shatter them. And also, you need to protect them from radiation. If any of those neutrons get into the magnets, it's going to damage it and it's going to stop it becoming superconducting. As soon as it stops becoming superconducting, it heats up. We get normal resistance and we get hot spots, and that will lead to magnet failure. If any of the magnets inside ITER fail, the entire experiment is over. There is no way to go in and cut the magnet out and replace it. They're built around the tokamak and there's no way to weld them. So if a magnet fails, it's all over. The magnets so this is one of the magnets in ITER that goes right around the reactor. There's a human inside it, just to show you the scale again. The magnets in ITER cost about $15 billion in total. They're about 2/3 of the entire cost of the reactor. That's how expensive they are. No magnets ever this powerful, this big, have ever been made before. So incredibly difficult and incredibly important. Okay, final thing I'm going to talk about, and then I'll shut up. The structural metals. This is what I work on. So it's the things that take that really high stress, really high heat right at the surface. So tungsten is our favourite because it's got the highest melting point of any element that we know of. Very high. This would be solid on the surface of the sun. So that's good. But it's brittle. That's the problem. So it's finding a way to make sure it's strong enough to survive the things we have to do to it. This is a diverter cassette. This will be eventually, for ITER, this will be coated in tungsten, and then it's built all of them around there, like that around the bottom. 54 cassettes, 10 tons each. That makes it twice the weight of a Boeing 747. So tungsten, very, very heavy, very dense, but quite cool. And the other sort of favourite material we have to deal with these is oxide dispersion strengthened steels. Now, sounds very boring, but it's actually quite cool. So what you have is a normal steel with sort of iron and chromium atoms sort of spread out as normal. Then you have tiny, tiny lumps of yttria oxide. Now, they're only 10 to 20 atoms big, so what do? Well, they do quite a bit because the interface between the metal and the precipitate, that oxide clump, is really chaotic. So those vacancies and interstitials I was talking about earlier, those defects, diffuse and they move to the interface, then they annihilate each other, they disappear. So these are basically little filters for our material that help us get rid of those defects and stop them building up and causing problems. The problem is we can only make about a pebble of it. It's very difficult to produce a material which has this kind of microstructure on a big enough scale. So at the moment, the biggest piece ever made you could hold in your hand, which isn't very useful to build a reactor. But it's coming. There's a lot of research going into that. Okay, so fusion, limitless, clean energy, the power of the sun on Earth. But can we build it so it lasts? That's the big question. So over to you. Any questions for me?